Hello people. Now, this is my attempt to make a video about the general binomial theorem. This is a year 2 topic in the A-level maths spec. It's building on top of stuff that you have seen in the AS spec in the first year of the course. It just gets more generalized so you can use it in more situations with different indices. And I'll show you some examples of that in action and how you might actually use it to approximate something. So the main aim of this is to actually use the formula for the general binomial expansion. So there's a formula, you've got to know it inside out, so you can just use it nice and smooth in the future, substituting various numbers into it. Now, if I write out the expansion in ascending power sub x for 1 plus x to the power of n, this is what you would have seen in the first year of the course. You would have seen this becoming n choose 0 plus n choose 1 lot of x plus n choose 2 lots of x squared, and so on. Notice how we've got the powers linked up every single time if we wish to specify it. Now, the funny thing is that this expansion can actually generalize to lots of different types of indices by avoiding this combinatoric notation. So, how many ways are there to choose 0 things out of a list of n items? There is one way. How many ways are there to choose 1 item out of a list of n things? There are n ways, and so on. So, I'm going to use that to generalize this concept. So, we've still got the same starting point, 1 plus x to the power of n, but now we can rewrite it as 1 for the first term plus n lot of x for the second term, and then we've got n choose 2. Now, that one's harder to think about from a standing start, but here it is. So n choose 2 can be written as n multiplied by n minus 1 all over 2 factorial. So double check your statistics knowledge from year 1 if you're not so sure about this bit. So anyway, I can stick this in as the coefficient of x squared. Now, this pattern continues, okay? You can write out each combinatoric thing as its own fraction involving n and something factorial. So here's the next one, for example. The next coefficient will be n multiplied by n minus 1 multiplied by n minus 2 all over 3 factorial, and we are going to multiply that by x cubed because it's the x cubed term. And it goes on forever. Now, this thing only works for small values of x. So it's for small values of the variable here. Now you might be thinking, what the heck is small in this context? Well, for our purposes, we want those values to be close to the origin if we were plotting it as a graph, for example. In fact, we want all of these values to be acceptable only if the modulus of x is actually less than 1. This is also known as the range of convergence, if you wish to Google it for more information. But even as a brief rule of thumb, keep that in mind. This is a criteria that you need to satisfy to be able to say that this can be expressed as this. Now, and one thing to mention, if you truncated this series, if you didn't bother with some of the terms, for example, you're only approximating now. It's no longer an exact equivalent thing. So You can use a wavy approximate symbol, written like that, as an equal signs but wavy, just to show it's approximate. So, let's have a look at an example now, using actual numbers. So, to find the first four terms of 1 plus x to the power of negative 2, the first thing to point out is that n equals negative 2. So, folks, with that in mind, I can find the first four terms using the general binomial theorem. So, I can say that therefore 1 plus x to the power of negative 2 can be approximately written as 1, following on from the formula, plus n lots of x, that's the second term, plus minus 2 multiplied by minus 2 minus 1 over 2 factorial lots of x squared. I can keep going on with these terms. For instance, I've got 1, 2, 3 terms. The next term is going to look like this. We've got n once again, multiplied by n minus 1, multiplied by n minus 2. It's a lovely countdown. It's a good way to remember that. The denominator of the coefficient is 3 factorial, and we're going to multiply it by x cubed. So, 1, 2, 3, 4 terms are present there. And if you expand and simplify this, the approximation can be written more easily as 1 minus 2x plus 3x squared minus 4x cubed. Now, this only works, like the criteria said, for small values of x close to the origin. So the modulus of x is going to equal 1. So we had that variable there. That thing there has got to be smaller than 1. Its size has got to be smaller than 1. Okay? Now, keep that in mind for the next example.